Hello everybody, I welcome you all to this session on behalf of School of Sciences. Now we are going to continue on CHE 2 Block 1 Periodicity and S Block Elements. So again we'll try to elaborate on this. Now why atomic number we are referring to? Please recall, because atomic number is the intrinsic property of the atom. The number of electrons on the outer part of the atom or the number of protons inside the nucleus, those are equal. Number of protons inside the nucleus is equal to the number of electrons in the extranuclear region. So the atomic number is the intrinsic property of the atom. So we are going to see how these atoms are built up. Okay, what are these made up of? Now this is the long form of the periodic table. These are the periods. Okay, the horizontal rows are the periods and the vertical columns are the groups. So this is the latest model of the periodic table, where you can see there is 1, 2, 3, 4, 5, 6, 7 periods, and you can see 1, 2 up to 18 columns. These are the groups. Okay. Now we are going to see how these periods are built up. See the first period. It is a very short period. Hydrogen and helium. Okay. Next comes the, again a short period, not a very short period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Now you see on the top of these atoms are written the atomic number. But what is the electronic configuration of the atoms? For this we must not only restrict ourselves to the periodic law. We have to extend to Pauli's exclusion principle and Hund's rule of maximum multiplicity. Okay. So what is Aufbau principle? That also we must recall. Now Aufbau principle is used to determine the electronic configuration of an atom, molecule or ion. Remember, we can also determine for an ion also what should be the electronic configuration. Now in this principle we remember that electrons fill orbitals starting at the lowest level possible. That is 1s before 2s. Okay. Now orbitals, they are filled according to the n plus l rule. Now what is n plus l? N is the principal quantum number and L is the azimuthal quantum number. The total n plus l is considered when we see which orbital will be filled before the other. That is, orbitals with a lower n plus l values are filled before those with higher n plus l values. Okay? But what happens when there will be same n plus l values for two orbitals? Can't you think of such cases? If you take the case of 5s and 4p orbitals, there in 5s it will be 5 plus 0. N plus L will be, N will be 5, L will be 0. 5 plus 0 is equal to 5. And for 4p, it will be, N will be 4 and L will be 1. So 4 plus 1 will again be 5. Then which one will be filled up first? Obviously, the one with a lower N value, that is 4p. You see, this is the Aufbau principle, where you will see 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p then 5s. Okay? So this is the n plus l rule. First the 4p will be filled up and then the 5s will be filled up. Similar thing you can see in case of 3p and 4s. So again we go back to the rule, n plus l rule. Orbitals with a lower n plus l value are filled before those with higher n plus l value, and in case of equal n plus l values, which were the things we saw? 3p and 4s, and again 4p and 5s. So I hope this is clear what is the n plus l rule. And also you must remember that an orbital cannot take more than 2 electrons. The number of electrons that can occupy each orbital is limited by Pauli's exclusion principle. What does Pauli's exclusion principle state? That no 2 electrons can have all the 4 quantum numbers similar. What are the quantum numbers? Principal quantum number n, azimuthal quantum number l, magnetic quantum number ml, and the spin quantum number ms. Now Pauli's exclusion principle states that 4 quantum numbers for 2 electrons cannot be similar. That is, if there is one electron with particular n, l, ml, ms, ms equal to plus half, then the other can have n, l, ml similar, but at least the ms must be different, that is, it should be minus half. Okay? So Pauli's exclusion principle states that no 2 electrons can have all the 4 quantum numbers similar, and in this way we can infer that maximum number of electrons that can be occupied in a particular orbital where n, l, ml will be similar. Where it can differ? It can differ only in ms, that is the spin quantum number. So if one electron has plus half, then the other electron has to have minus half as the spin quantum number. So this is a direct outcome of the Pauli exclusion principle. If multiple orbitals of the same energy are available, Hund's rule says that unoccupied orbitals will be filled before occupied orbitals are reused. That is, if in the same level you have multiple electrons, suppose like this, in n equal to 2, there are 3 p orbitals. Now, if there are 3 available electrons here in this level, then first one electron will enter this px, then py, then pz. It won't be that 2 electrons, the direct outcome of Pauli's exclusion principle we know, maximum number of electrons that can be occupied in a particular orbital is 2. So if we put 2 here and 1 here, 1 electron here, 2 with opposite spin here and 1 with opposite spin here, well, that case will be wrong. First, one electron will enter px, then another in py, and then another in pz. This is Hund's rule of maximum multiplicity. Now, see, these are the atomic energy levels. For n equal to 1, we know L will be only S, 1s. N equal to 2, L will have S value and P value. N equal to 3, L will have S, P, D. N equal to 4, L will have S, P, D, S. Okay? This is why, because L has value 0 to n minus 1. So, L will have the value of 0 and 0L denotes S orbital, that is spherical orbital. So, for principal quantum number 1, there will be only 1 and only 1 orbital, that is 1s. Now, for n equal to 2, 0 and n minus 1 will be the values of L. 0 and 2 minus 1, that is 1, will be the value of L. Now, for P, there can be 3 different configurations, so 3 orbitals. We'll come to it later. So, Similar for n equal to 3, 0, 1 and 3 minus 1, that is 2, that will be the maximum level. For n equal to 4, 0, 1, 2 and 3, that will be F. Okay. Next, again I will repeat the trends in electron filling. 1s, 2s, 2p, 3s, 3p. Now see, after 3p, instead of the 3d level being filled up, it will go to the 4s level. Why? Because 4s is nearer to the nucleus and 3d is further away from the nucleus. Is it clear? And also the n plus L rule you must remember. Again you see, from 4p, instead of going to 4d, it will go to 5s and then to 4d. Again 4d, instead of 4s, from 4d it will go to 5p, then 4s, then 5d. Are you finding this diagram a bit difficult to remember? Well, there is an easier form. You can just write the orbitals one after the other. 1s, then below that you write 2s, 2p, below that you write 3s, 3p, 3d, 4s, 4p, 4d, 4s. Okay, one after the other you write 5s, 5p, 5d, 5s, 6s, 6p, 6d, 7s, 7p. One below the other you write down. Then you just put the arrows like this diagonally. So whenever you write down the electronic configuration, you first write down 1s, 2s, 2p like that. I always find it easier. Okay. Now in this way, if we come to see what is the configuration of the hydrogen atom, it is 1s1. Now for hydrogen, of course it is a gas, it is the lightest element, and you can also see this is hydrogen gas kept in a cylinder. Now it occupies it has no odor, no smell and no color. And what is dangerous about hydrogen gas is that previously balloons were made up of hydrogen gas, but nowadays it is not done so because there would be tremendous accidents. So nowadays the safer helium is used instead of the hydrogen gas. Also you can see that it easily catches flame, and that is another difficulty with hydrogen. But the most important use of hydrogen is in ammonia synthesis. Next we go to helium. Okay. Now first period has the only two elements, hydrogen and helium. This one has 1s1, and so obviously the other one will have 1s2. So in the first period only the 1s electrons are being filled up. There is no complete octet being developed here in any of the atoms. Instead a duplet, which you will see for helium, and it is also colorless gas. Another thing for helium, as I told you, it was discovered by Sir William Ramsay and independently by Cleve and Langate in 1895. The name, the origin, comes from the Greek term helios, sun. It is a colorless, odorless gas that is totally unreactive. So we come to the second period, which is also a short period but not a very short period. The first one is lithium. Now remember, in this level, first the 2s electrons will be filled up one by one, and then the p electrons will be filled up. There is no d level in the second period also. So we come back to lithium. The electronic configuration, you see, it is the core is of helium, 1s2. You can write it in this way also. In square brackets, you can write helium. It denotes the configuration of helium, and with that you write 2s1. Now this is the crystal structure of solid lithium. The body-centered cubic structure is the most stable form for lithium metal at 25 degrees centigrade. And remember that for all alkali metals, that is the group 1 elements, these are based upon the body-centered cubic structure. Next, atomic number 4, electronic shell 1s2 2s2. Now if we go on more on beryllium, you see this is the color of beryl. Next we come to boron, and if you go back to the periodic table, you see from here the 2p levels are being filled up. Okay, so boron has the core structure as helium, and then outermost valence electrons is 2s2 2p1. This is the crystal structure of solid boron. Next we come to carbon, atomic number 6. Now this is very interesting, because in carbon you will see a direct outcome of the Hund's rule of maximum multiplicity. You see, this is atomic number 6. So instead of the p electron, second electron entering this p level and making a pair, the second electron enters the py level. So px level first fills up for boron, and then for carbon, the second electron, instead of pairing the px, it first fills up the level which is in the py orbital, which is in the same level in terms of energy as px. So you can see Hund's rule of maximum multiplicity being obeyed. Now carbon is something which occurs as graphite as well as diamond. One is not so precious, and not precious at all, you may say, compared to diamonds, which are billions and billions and millions of rupees worth. Graphite and diamonds are the allotropes of carbon. One has sp2 hybridization and another has the sp3 hybridization. Next we come to oxygen. So what will be the electronic configuration? Outermost there is 6 electrons, total 8. So the helium configuration, and with it 2s2 2p4. Okay, so the one more electron will be pairing the px. Up to nitrogen there was 1 1 1 in each p level. Then what happens? Okay, first px, py, pz. Then for nitrogen what happens? Another electron will enter this pz. Boron, carbon, nitrogen it becomes. Then for oxygen, one more electron, it enters the px level. Okay, so here the pairing occurs first. Next we come to fluorine. Fluorine electronic configuration is also very interesting, because you see there will only be needed one more electron, 2s2 2p5. So if there is one more electron, it will have the inert gas configuration of neon. So for alkali metals like lithium, sodium, potassium, you will see there is ns1 electron. Okay, the outermost valence shell has one electron in the s level. So for the alkali metals, they will readily try to give out the electron and form a cation. But for halogens, it is just the reverse. Okay, here it is ns2np5 electronic configuration, and so if it just takes up one more electrons, it will have ns2np6, that is the octet will be complete, and then the halogen will readily try to take up one electron and form the anion. So for the left side of the periodic table, you can infer cations are formed easily, and on the extreme right, the anions are formed very easily. So next we come neon. Neon, of course, after fluorine, it will have ns2np6, 2s2 2p6 will be filled, a stable octet structure, and so it will be unreactive just like helium. Next we come to the third period, and it starts with sodium, and sodium imparts a orange yellow color to the flame. Electronic configuration, it will be 3s1, and the structure will be of course again BCC as it is for the alkali metals. Next, magnesium and aluminium, 3s2 3p1. Here the p electrons are being added, entering the p level for aluminium. Okay, so this way we can go on. We have discussed the electronic configuration depending on the Aspirants principle, Pauling's exclusion principle, Hund's rule of maximum multiplicity for period 1 and 2 we have done in detail. Period 3 is also similar to that of 2. Now in period 4 if you go, okay, so after calcium electrons enters the 3D level. So from scandium to zinc, these are 3D levels are being added, and so these are the transition elements where the D electrons are being added. Okay, now here you will see some interesting things like chromium. Chromium, it should be 3d4 4s2, okay, but it is 3d5 4s1. Why? Because half filled 3d5 is more stable. So chromium attains the configuration of 3d5 4s1. Okay, so we must also remember these cases where it is not obeying the usual path. Okay, so another case is copper. Copper, if you go, you see it should be 3d9 4s2 following the above principle, but instead it is 3d10 4s1 because full filled is more. The 3d10 as a full filled orbital will be more stable than nearly filled. Okay, so for chromium and copper, these two cases you must remember, because in these two cases it does not follow the usual rule. And then again the p electrons are being added after 3d10 being filled up, and 4s2 in zinc is again the electrons being added in the 4p levels for gallium, and up to krypton it ends as 4p6. Next we come to the fifth period. Fifth period, you see it is from rubidium to xenon. Again the electrons are being added in the 4d level starting from 39 to 48. So these are also similar in case as of fourth period. Next we go to the period 6. What is happening here? You see for lanthanum 57, instead of the electron being added to the 4f orbital, it goes to the 5d level in lanthanum, and then for the rest it adds to the 4f level. Okay, so lanthanides are coming here from cerium to ytterbium, or all the 4f 14 electrons are being added here, but not in the case of lanthanum. Here instead of going to the 4f, it enters the 5d because both have similar energy. Okay, and then one by one all the 14 electrons enters the 4f orbital from cerium to ytterbium. And then again from lutetium the d electrons being added, 5d electrons are being added one after the other. Okay, then again the 6p electrons are being added from thallium to radon. Then if we go to the seventh period, here instead of the lanthanides we will find the similar actinides, okay, where the f electrons are being added. So in this way you see this arrangement of periodic table where we have two rows at the bottom is much more convenient. If we had to put all these elements inside this table, then it would be very much crammed, and it would have occupied in such a small space, it would not look good. So this way it is better. All the lanthanides and the actinides are kept separate, where the 4f level and the 5f level electrons are being added. So if we classify the periodic table by sub-levels, we see on the left are the s orbital electrons being filled up first, extreme right p orbital electrons filled up first in the last valence shell, and in the middle there are the d orbitals being filled up in the extreme level valence electrons, and just at the bottom there are the f electrons. So just by looking at the periodic table, you can say where are the s electrons, where s orbital electrons being filled as the valence electrons, where are the p levels, where are the d levels, and where are the f levels. Isn't that great? Now we must remember the electron arrangement also. You should recall that there is the neutron and proton inside the nucleus and the electrons outside the nucleus. High speed electrons moving all around the positively charged nucleus, where the neutrons have no charge but the protons have positive charge. And this is of most importance, that for each row or period a new layer is being added. 1s, 2s, 3s. So as you go down the rows, the periods, a new layer is being added. So as you go down the group, a particular group, say the alkaline earth metals, lithium, sodium, potassium, rubidium, as you go down, then what will happen? The outermost electron will go further and further away from the nucleus. And so this you must remember, and we will continue from this topic with periodicity of the elements. Okay? Thank you.